Hello, my name is Burdess, and this is my research partner William Hutchinson. We're from the departments of Mechanical Engineering and Electrical Engineering, respectively. Our faculty mentor is Dr. Zhou from the Department of Mechanical Engineering and the AM3 lab. For our project, we are tasked with designing a low-cost and easily manufacturable SCARA arm for swarm-based 3D printing. A SCARA arm is a robot arm architecture that consists of two joints, a shoulder joint and an elbow joint like a human arm. This allows it to reach out over a build platform and interact with the workpiece. Specifically for 3D printing, it reaches out with a hot end that pushes out molten plastic in a layer-type structure to build up an object. A SCARA arm allows for technology called swarm-based 3D printing, where multiple printers work together on one piece. This allows for a really rapidly rescalable factory environment. So if one day you need a very large object printed, you can have 20 or 30 printers working on that one object, whereas if you needed lots of small objects, you can split those printers up to work on those small objects or anywhere in between. But the problem with this architecture is that each arm adds in costs. So if you need 20 or 30 arms, it's 20 or 30 times the cost of one printer. So each kind of design decision and cost multiplies across your printers. The main cost of the current ARM design that AMBOTS has is time. So it consists of a lot of 3D printed components that take, in total, 2 to 3 days to print. So we were tasked with designing an ARM that minimizes the 3D printing time by using off-the-shelf components and traditional manufacturing processes wherever possible. Taking the design back to the basics, our design schema consists of rigid axles and plates to build up the structure of our arm. We did a finite element analysis on this arm, and where it's fixed on the axle here, and with 200 pounds of load on the end, we only saw a deflection of 1 millimeter. So our design in the end was very rigid, and we're going to kind of talk about the design in a second. One also concern of this arm design is that is kinematics. So any error in the joint here is multiplied when you bring it out over a length. So a kind of deflection here of 1 millimeter can multiply up to 10 millimeters or whatever at the end. So to multiply the accuracy of our stepper motors, we had to add gearing to them, add a gear ratio. And to get the desired accuracy, we decided that we needed a 25 to 1 gear reduction. So that kind of increases the complexity of our design, and so we decided on a 2-pulley system. So that's the pulley you see here. We designed our arm in Fusion 360 in a CAD software, and once we had our design, we went to manufacture it.
So to manufacture it, it's very simple since we used off-the-shelf parts. So our total bill of materials was around $200, and that's about the right amount for a low-cost 3D printer. So that meant that our design was very cheap comparatively, and we used aluminum extrusion for the metal, and we used acrylic plates for our plates. And what that allowed us to do was make everything basically in-house. So you can just order a long length of aluminum extrusion, cut that down, CNC machine the acrylic plates, and then 3D print those parts. And those 3D printed parts only totaled about 8 hours on the printer. So that was a drastic reduction in time. And to test our arm, we affixed it to a wooden jig. We did not have an extruder or Z-axis because we felt that that wasn't needed to test it. So we basically had that arm working as a pin plotter. So if you have a pin plotter and it can plot things, then it can 3D print. And when we went to test it, we had it draw an intricate design, and in our case a fish. And whenever we drew that fish, we actually had it go over itself again. And when we did that, we noticed that the lines were perfect. So it went over itself perfectly, which meant our design was both rigid and precise. And with that, we were able to conclude that our design was indeed a valid replacement for the AMBOTS arm, and further research would include taking that arm and obviously making it work with their environment. So adding an extruder, adding in a base plate, and being able to mount it into their system and actually print parts.
And you can see here on the bottom right that we really achieved our goal of reducing 3D printed parts. So we only have 4 3D printed parts when compared to this large pile of 3D printed parts for AMBOTS. That's all the time we have, so thank you.